Alrighty, good morning, lads and ladies. Welcome back to MAC 1140 pre-calculus. Today we are going to pick up where we left off last time. Last time, you may remember, we introduced exponential functions. We talked about their graphs and their symmetries and their asymptotes, their domain, their range. We talked a little bit about how quickly they grow or decay, and how you can tell based on the algebra of the function whether it is growing or decaying. Today, I aim to solve a few more problems with exponentials and then introduce a special number. So let's get to it. There we go. Turn screen share, get the document camera running. Hope everybody had a safe and fun Halloween. If you're here in Gainesville these days, the weather has just been amazing. A little bit chilly. Very pleasant change. So here is MAC1140 section R1, which is pre-calc. And today is the 1st of November, 2021. Today, more with exponential functions. I haven't had my coffee yet, so my brain is just a little bit slow. More with exponential functions. The number e, that's that special number I mentioned. And we may introduce logarithms. We'll probably get there. Like I said, these sections go really quickly. Oh, let's get this focused. These sections go very quickly because this is stuff that you guys have seen in previous algebra classes. We don't want to burn a shitload of time on it. There's one place here where we're going to slow it down just a little bit, and that's when we talk about properties of logarithms, the algebraic properties of logs. I think that's something that even the most well-intentioned college algebra students don't quite master in that class, and I think it's worthwhile to take the time and make sure we do that at a pace that you can sort of absorb. But besides that, we're going to be moving quite quickly now. One or two problem types that I'd like to look at before we dig in there, and I'm going to grab your book so I can pull a few examples. So let's do this shit. No, almost. Yeah. Okay. So we didn't miss any theorems from the previous section, but there are some kind of classic problem types beyond the basic graphing stuff that I just want to take a quick look at with you. Good news, we're not going to be messing around with the compound interest stuff that much. I will do a few problems with compound interest, but only in the simplest way. And I'm not going to require you guys to memorize that formula. I don't think that sort of memorization is very helpful. But let me see here. Well, maybe your book doesn't have any of these. I was thinking, like, why didn't I see any of those when I set up your homework? And perhaps it's because they're just not here. Yeah, they're not. Okay, well, there is a problem type that I want to share with you, even though it's not in your textbook. These are such classic problems. It's something you need to know how to do. So you had a few problems in your homework that asked you to match an exponential function to a graph, right? And the intent there was for you to think about transformations. You say, okay, this looks like 2 to the x, but it's been shifted up by 1. So this is 2 to the x plus 1, that sort of thing. There are some other problems sort of like that. Here's one that's not too far off from that I'd like, yeah, that you guys need to know how to do. So here we go. So you had one like this in your homework. I shouldn't say match. Find the function f of x a to the x, graph below. And the graphs look something like all those exponential graphs. Something like this. So we have this horizontal asymptote, y equals 0. I'm going through the point 0, 1, and 2, 9. And we want to find the function of the form f of x equals a to the x, whose graph this is. And really, we've got two pieces of information here. I've got this point and this point that I can work with directly, plugging numbers in here and trying to find a. If you plug this point is 0, 1. This is going back to some chapter 2 stuff. Since the point 0, 1 is on the graph, what is f of 0? I can say what f of 0 is. Who remembers how to do this?
Would it be 1?
Yeah, exactly, right? Every point along the graph is of the form, a comma f of a, right? Some number comma f of that number. So 0, 1 being on the graph means f of 0 is equal to 1. And then I can take this and plug this in, right? F of 0, that's this thing, both x replaced by 0. This means a to the 0 equals 1. But this doesn't really give me any new information because a is just a constant and any constant to the 0 is equal to 1. This is true, so this is just the same as saying 1 equals 1, which is always true for any value of a. But I'm going through this step because there's some related problems, some similar problems to this one, where using this information is actually really important. And I'll show you one of those in a minute. The other bit of information I have here is that the point 2, 9 is on the graph. So 0, 1 didn't really help us at all. But let's see what happens with 2, 9. Since 2, 9 is on the graph, f of 2 has to be equal to 9. I'll go through the same thing. F of 2, well, that's what I get when I plug x equals 2 into the formula for f. So that's a to the 2. So this looks like a to the 2, or a squared, equals 9. How do I solve this equation?
Does that say 2, 4 for the bottom coordinate or 2, 9?
Sorry, 2, 9.
Oh, okay.
Take the square root.
Yeah, that's one option, right? We can either subtract the 9 over and factor, or we could take square roots on each side. There's one catch here, and that's if you're going to solve this by taking square roots, you got to remember the plus and minus. So remember, anytime you take square roots on both sides of an equation, you get a plus and minus. Right? There's two numbers for a that solve this equation. Those are the positive square root of 9 and the negative square root of 9. So it's positive and negative 3. All right, if you were to plug positive 3 in here, positive 3 squared is 9. That's true. If you were to plug negative 3 in here, negative 3 squared is also 9. So I've got these two solutions, but only one of them is going to give me the function that I have graphed here. Which one should I take and why?
+3 because we're looking at the top right.
It's true that we're going to take the +3. What do you mean by looking at the top right?
I just meant if the graph was split into 4 hemispheres, you'd be looking at the quadrant 1, which is the top right of all 4. Or on this side, it would just be the right side, period.
I think I see what you mean.
Right of the y-axis.
Right. So yeah, this is definitely quadrant 1, and that means both x and y should be positive. But the a here is neither x nor y. It's neither of those things. It's the base of the exponential. And the real reason we use a equals 3, not a equals -3. And I understand what you're thinking, right? Because over here, everything is positive, so we should use the positive value of a. In quadrant 1, every coordinate is positive. But the real reason we're sticking with the positive value for a and not the negative value is because if you look back at the definition of an exponential function from last Friday, we said that the base always has to be positive. And that's to avoid imaginary numbers. So it's not necessarily that if we use the negative value for a in this function, we would be spitting out negative numbers over here or anything like that. It is true for some integers that we would, right? That's fair enough. If you were to plug in like x equals 1 after using a equals -3 here, you would get -3. But really, we can never have a negative base in an exponential. Yeah, so I guess either way of thinking about it is fair. I don't want to say that that your logic is incorrect. If we tried to use a negative value for a, then for example, the point we would get when we plug in x equals 1 would be 1 comma -3, which would be down here. That is true. But there's a deeper reason, and the deeper reason is if you use a negative value for the base of an exponential function, what happens when you plug in 1/2 for x? You'd have -3 to the 1/2 power, which would have an I in it, right? That would be I times the square root of 3. Anytime you use a negative number as the base of an exponential, this thing's going to spit out lots and lots and lots of imaginary or non-real complex numbers. And that's really not okay. We want these functions to be able to take in all real numbers as their inputs, and we want them to spit out positive real numbers as their outputs. We don't want them spitting out non-real complex numbers. So here the function is f of x equals 3 to the x. If you prefer to think about it the way you did, that will get you to the right place as well. So I don't want to say I'm correcting you. I just want to point out that there are other reasons also. A little note. Most textbooks and most math people would say that exponential functions are a broader category of functions than just a to the x. That's how your book defines them, and that's fine. There's nothing wrong with that. And those give you the sort of basic family of exponentials. But generally, we'd say you can multiply by a constant. So I'm going to change this just a little bit. And rather than giving you the graph here, I'm just going to give us a couple of points that should be on the graph. How about yeah, how about this? So here, instead of saying my function is just a to the x, I'm saying it's some constant times a to the x, which would be a classic transformation of the regular a to the x, right? It's a vertically scaled version of a to the x. But this is sort of the way most people define exponential functions. They say it's some constant times a to the x. And this constant sometimes is given a special name. It's sometimes called the initial value, for reasons you'll see in just a second. And let me add here and sketch the graph. Of course, if I just gave you the graph and I made sure to put the point 0, 3 and 2, 3/4 on there in a way that you could read them, then you could find the function the same way. All right. Any ideas what I can do here? The 2 bits of information I have, just like the 2 points from the previous problem, are this and this. Really, the only information I have here is this and this. So we better make use of that. Let's start with this. If f of 0 is equal to 3, that means when I plug 0 in for x here, the whole thing should be equal to 3. So since f of 0 is equal to 3, we have f of 0, well, that's c times a to the 0 equals 3. And remember, a is just a number, it's a constant. So a to the 0 is 1. So this is c times 1 equals 3, i.e., well, c times 1 is just c, right? So this is c equals 3. And I can take this bit of information and update my trial function here. So f of x is 3 times a to the x. I still don't know what a is, but I found c, and I can take that information and plug it in. Now I can move to the second point. Since f of 2 is 3/4, 3 times a squared is 3/4. And again, I want to solve for a. Who can tell me what a good first step here would be?
Get the 3 on the other side.
Yeah, let's ditch that 3 on the left. So I'm going to divide both sides by 3. I'm going to write this down like this. I'm going to force us to deal with these fractions. How do I clean up that? Forget about the a squared on the left. We'll get to him in a minute. What is 3/4 divided by 3?
Don't you take the reciprocal and multiply them?
Yes, take the reciprocal of what though?
3/1 and make it 1/3.
Very good. So the trick to this, and I see even calculus students mess this up from time to time. I just want to emphasize here. We need to take the reciprocal of the bottom and multiply by that. So you need to interpret that bottom as 3/1. In other words, sort of, this is our big fraction. And if I'm going to divide the one thing by the other thing, I need to think of the top and bottom of the big fractions as each being little fractions, so I know what to do. Since the little thing downstairs is just a 3, I must think of that as 3/1. And then I realize, oh, okay, I take the reciprocal of this, right? Leave the top alone, multiply by the reciprocal of the bottom. So that's got to be 3/4 times 1/3. And what is that? What is 3/4 times 1/3?
3/12.
But we can think about it a little bit more sophisticated. It's true that that's 3/12, and then we could simplify that, and that will get you there. But isn't it nice to just say, okay, I can cancel these. They're multiplying. There's a factor of 3 upstairs and a factor of 3 downstairs. And 3/12 is the same as 1/4. You just have to factor the 12 as 3 times 4 and then cancel the 3's. All right. So let me rewrite this as a separate line. I arrive now at a squared equals 1/4. How do I solve this?
Would we not square 1/4 or not?
Something like that. So the object on the left here is a squared, and I want to solve for a. So it's not that I want to introduce a new square. I want to get rid of this square. So just like when I had a squared equals 9, we took square roots on both sides. I can now take square roots on both sides, and I get a equals plus or minus the square root of 1/4. Which might feel a little wonky, but I promise you it works just fine. The square root of 1/4. Remember, square roots play nice with multiplication and division. This is the square root of 1 divided by the square root of 4. The square root of 1 is 1. The square root of 4 is 2. So this is plus or minus 1/2. And if you think about it, 1/2 times 1/2, that is 1/4, right? So yeah, the square root of 1/4 should be 1/2. And it is. And again, we take the positive version. Because the base of an exponential is always positive. So f of x here, I knew it was 3 times a to the x. And now I know that a is positive 1/2. So this is 3 times positive 1/2 to the x. And it's important when you have an exponential like this that you put the base in parentheses to make very clear that the 1/2 is raised to the x, but the 3 is not. Okay. Any questions on how we found this guy? Here's a, and that means here's my function. Any questions on the notation or the procedure? We did give ourselves an additional task here, and that was to graph the function. We want to sketch the graph. So can you tell me a little bit about this exponential? Is it a growing exponential or a decaying exponential, and why? Remember when we talked about this on Friday? How you can tell whether your graph is going to look like this or like this.
Decaying.
Very good. This is a decaying exponential. Because a is smaller than 1. Right? If the base of your exponential is smaller than 1, then it's going to be a decaying exponential. You can think about it like this, if you don't like memorizing that. If you multiply a number smaller than 1, like 1/2, by itself again and again and again and again and again, which is what happens here as x gets bigger, right? When x is 2, you've got 1/2 times 1/2. When x is 3, you've got 1/2 times 1/2 times 1/2. When x is 4, you've got 1/2 times 1/2 times 1/2 times 1/2. When you take a number like 1/2, a number smaller than 1, and you multiply it by itself over and over again, it gets smaller and smaller and smaller, right? 1/2 times 1/2 is 1/4. 1/2 times 1/2 times 1/2 is 1/8. 1/2 times 1/2 times 1/2 times 1/2 is 1/16. So the top stays 1, but the bottom gets big, which makes the whole thing get small. So this is a decaying exponential. So its graph is going to have that shape of a decaying exponential, which means it approaches the horizontal asymptote y equals 0 over here on the right. And you can just draw that general shape, and then we'll come in here and label some points. What sort of points can we say for sure are on this graph? Let me bring us back to the statement of the problem itself.
0, 3.
Yeah, 0, 3 has to be on this graph because we were told f of 0 is 3. Also, 2, 3/4 has to be on this graph because we were told f of 2 is 3/4. I'll use 0, 3 for sure. That's my y-intercept. If I call this 1 right here, right, so we could label 2, 3/4, and that would be okay. But what's the point where x is equal to 1? What is f of 1? They didn't tell us at the start of the problem, but I have this function now. So if I want to know what f of 1 is, I would just plug 1 in for x here. And that would be 3 times 1/2 to the 1.
Would it be 3 over 2?
Yeah, exactly. 3/2. Yep. So for my other point here, I'll use 1, 3/2. And we could use 2, 3/4 just for shits and giggles. If I want a third point over here where x is -1, what would that be? This may be a little trickier. I'll annotate here. F of 1 was 3 times 1/2 to the 1, which is 3/2. Over here, f of -1 is 3 times 1/2 to the -1st. And I don't want to write it like this. This is an integer, so I'd like to write it more nicely. How do I find 1/2 to the -1?
We not plug it in for x also, or no?
Oh, yeah, so we did plug in for x, right? I plugged -1 in for x here. And that gave me, maybe I wrote it a little too small. That's 3 times 1/2 to the -1. So I plugged a -1 in right here. Maybe I misunderstood the question, but my goal is just to simplify this.
Isn't that 2?
It is. It is. Remember, a number raised to the -1 is the reciprocal of that number. So 1/2 to the -1. That's just 2. So this is 3 times 2, or 6. So we'll point over here where x is -1. It's -1, 6. All right, this is a beautiful graph. Got our asymptote. We've got 3 points clearly labeled. And instead of giving you those bits of information at the start, I could have given you this graph. And from the graph, you could also come up with this formula, just like we did on the first example. And those are classic problems. Those are problems that pretty much everybody sees at some point when working with exponential functions. So I just wanted to share them with you. Okay. the next topic for today is the number E. And usually this is motivated by talking about something called compound interest. And anybody who's ever struggled with a credit card or student loan knows that compound interest is a bitch. Similarly, rich people know that compound interest can be your friend. Or if you've seen the movie Back to the Future, where Marty McFly has some small amount of money in his bank account in the year 1980 something, time travels into the 2020s and discovers that he's a very rich man. It's due to compound interest. It's due to the fact that these exponential functions grow very, very quickly, and that compound interest is actually an exponential function of time, meaning there's some function of the form c times a to the x for every compound interest scheme. Again, the formula for it is not a very pleasant thing to work with. It has a lot of constants in it with silly names. And it's not my intent to make you memorize a bunch of formulas, but I do need to show this to you. So I elected to not give you any problems with compound interest in your homework because I just find it a little bit annoying. And everybody always gets nervous about memorizing the formula. So I'll just show you the formula here, and we're going to deduce some stuff from this. All right, I'll explain what each of these symbols means. A of t on the left, this is the amount after t units of time. And by amount, I mean either the amount you owe or the amount in your account, right? It's if I borrow some amount of dollars and then t years later, I want to know how much I owe, I would plug in whatever for t. And this would be the amount that I owe. P here is called the principal. That's the original amount of money you borrowed or the original amount of money in your account. It's what you start with. P here is like C from the previous problem. R is the interest rate, and it's often called the nominal interest rate. N is the number of compoundings. I'll explain what that means. Number of compoundings per unit of time. And you see me being very careful there. I'm not saying per year or per day or per month. And over here, I said after t units of time. So it depends on how you're measuring time. The number n changes if you're measuring time in days versus measuring time in weeks versus measuring time in years. Most compound interest problems usually have time measured in years, but there are some variations on that. And t, of course, the variable t, is the time since borrowing or depositing the principal. And it's usually measured in years. But sometimes measured in other units. So here's how this works. If I tell you I'm going to borrow $1,000 at the nominal interest rate of 5%, compounded monthly, then I would plug in 1,000 for t. What did I say, 5%, so 0.05 for r. And if we're compounding monthly and measuring time in years, that means I'm compounding 12 times per year. So you would plug in 1000, 0.05, and 12 for P, R, and N respectively. And that will give you some function that tells you how much I owe the bank after T years. All of that is, I think, kind of boring. Really, the interesting thing here is what happens when you study this as a function of N, which we will get to. But I want to explain what compounding means. So this compound interest formula is usually thrown at you at some point in your math career. But way back in the day, you probably saw something called simple interest. Have you guys ever heard of simple interest before? If you ask someone on the street, how do you calculate interest? Most likely they'll give you an answer that comes from simple interest. You just multiply the amount borrowed by the interest rate and the time, right? So the interest earned after T units of time is the amount borrowed times the interest rate times the time. And P, R, and T are the same thing here. Principal nominal interest rate. Nominal just means the named interest rate. It's to contrast it with something else, a different kind of interest rate. And T, of course, is the time. So here's what compound interest is. I'm not going to go through a bunch of shit here, but compound interest is what happens, or what you get, when you use the simple interest formula, but you check in kind of regularly to see how much you owe. So compound interest is the result of checking in to calculate the interest earned sort of so far a bunch of times instead of waiting to calculate interest when you pay back the loan. So basically, here's how it goes. Imagine you're a banker in year like 1500 or some shit, right? I know this might take a little bit of creativity, but imagine you're like a pre-Renaissance, Renaissance era banker. You loan money out, right? That's kind of what banks do. That's how they generate revenue. They loan money out and they charge interest on those loans. If you're a banker, you want to know how much everybody owes you, but not just like when they come back to pay the loan, right? You don't want to say, okay, Joe came back today, so I figured out how much interest he had on his loan, and he paid me back the principal plus that interest. You don't want to wait for people to come back and pay you the loan money back to figure out how much they owe you, because as a banker, you want to know how much is my business worth at any given moment. Right? I want to be able to tell people, yeah, you know, all these people together right now, I've loaned them out all this different amount of money, but I don't know how much interest they're going to have to pay on it until they come back. So like, I'm kind of fucked with figuring out what my net worth is right now. Instead, what you want to do is calculate how much everybody owes you like every day. So every day you go through all of the loans you have and you use this simple interest formula to calculate how much they owe you. So I'm actually going to write this down, and I want you to write it down as well. Imagine you give out a bunch of loans. And every day you calculate how much all these people owe you. Right, that will tell you how much your business is worth. Right, I've loaned money out to 15 different people. I don't expect any of them to come and pay it back today, but I want to know how much they owe me today. So I calculate the interest on their loan as it is today using this simple interest formula. That will tell me how much everybody in town owes me. So how valuable my business is on that day. What do you think a banker would then do with that information? So, Sam, Joe, Billy, Bob, everybody borrowed money from me. They all borrowed it at some interest rate. And on this day, I calculate the interest that each of them owe me. And I add that to the principal. That's how much each of those people individually owe me. That's how much I expect to get back from them if they were to come in today and pay back the loan. Well, if you're a smart banker, what you do is you take that amount of interest and you add it onto their loan, right? I just calculated how much money you would owe me today if you came in and paid me back. So rather than just throwing that information away, you add that onto the book. You say, okay, today you owe me the money you borrowed plus the interest that's accrued so far. You write that number down. That's the amount of money they would owe if they came back in and paid you today. So you give out a bunch of loans. Every day you calculate how much these people owe you. After doing that calculation, using simple interest, using this formula, I equals PRT, you add that to their balance and close for the day. Then you go home, you tell your wife, your husband, hey, we're in pretty good shape. If everybody were to come back and pay their loans today, this is how much money we would get. Here's the interest that they have accrued so far. So the total amount of money that they owe me is that interest plus the original amount that they borrowed. Reasonable thing to do. Well, the next day comes around. And again, you want to know how much money is your business worth. So you take the number from that book, the number you wrote down at the end of the previous day, and you run this simple interest calculation again. It's been one more day, so you add on the interest that they earned that one day, and you write that down in the book and you close for the day. You do the same thing the next day. And every day. Do you know what you've just done? You just invented compound interest. Compounding daily. That's what it means. That's what compound interest is, right? You calculate the interest they earned or accrued that day. You add that onto their account. If it's a savings account, you're giving them money. If it's a loan, you're saying, okay, you owe me this much now. You calculate the interest earned or accrued each day, and you add that onto the principal. And then the next day, you treat that new number as the number you're working with. It's the amount they owe you. So every day you calculate how that account has changed, right? How much interest has piled into that account each day, and you use that as the new principal moving forwards. This is called compound interest. So compound interest is where you kind of check in or calculate the amount of interest, simple interest earned every day. Or maybe you don't do it every day. Maybe you just do it once a month. Maybe once a month you go through your books and you say, okay, all these people have accrued this much interest. I'm going to add that onto their balance, and then we'll do it again next month. That's compounding monthly. Now, I said to imagine you're a Renaissance era banker, right? 15th century or some bullshit. One, these motherfuckers don't have calculators. So this takes some time. So they would have been compounding monthly, weekly, something like that. Let's move to the Civil War era, 1800s. At that point, you've got the Industrial Revolution. You have calculators, not good ones, but mechanical calculators. And you've got stocks, and you've got a very active market. You're starting to see modern financial systems develop. So at that point, a bank wants to know how much they are worth, and definitely at least once a day, maybe more like once an hour, right? Because the stock market fluctuates through the day. They want to know how much they can, in theory, invest or leverage. And as you move into the 20th and 21st centuries, financial institutions don't just want to know how much they're worth every month or every week or every day or even every hour. Those motherfuckers want to know their net value at every second of time. So what they want to do is calculate how much interest has accrued on all of the loans they've given out, not checking in and compounding once per day, not compounding once per week or hour or month. They want to do it at every second in time. So let me go ahead and first describe what's happening here. You give out your loans. Every day you figure out how much people owe you. After doing that calculation, using the simple interest formula, you add that to their balance and close for the day. You do this every day. This is compound interest with daily compounding. So here, n would be 365. Remember, we said we usually measure time in years, and n is the number of compoundings per unit of time. So if 1 unit of time is 1 year, and you're compounding every day, that means n is 365. And what people realize is that instead of using this I equals PRT formula and actually doing the calculation every day, that gives them the same thing as using this formula and plugging in 365 for n, right? The other variables are the same. You've got P, the principal, R, the interest rate, and T, the time. I'm saying literally, if you use this formula every day and calculate the interest accrued so far on a loan with principal P and rate R, if you use this formula every day, update that account, that's the same thing as plugging in n equals 365 to this function. And then you don't have to do the calculation every day. So some clever bankers figured that shit out way back in the day, pre-Renaissance. Moving into the post-industrial revolution era, banks, financial institutions in general, wanted to know their value at every moment in time, not just compounding once per day. Modern banks need to know. And you and I want to know, right? When I go look at my student loan, I don't want to be surprised by that number. I don't want it to update like once a month or once a year. I want to know exactly how much I owe at that moment. So modern banks and you and I and everybody in the modern world want to know the value of their assets at any moment in time. That means I want to do this check-in, this compounding, this calculation, not just once per day or once per hour, once per minute. I want to do this continuously. So if you're checking in daily, n is 365. If I want to know how much my assets are worth at any moment in time, this means I want to use n equals infinity. I don't want to check in once per year. I don't want to check in 365 times per year. I want to check in at every moment, every instant in time. That means I'm compounding now. So how many compoundings is that per year? Well, if you're literally going to do it at every moment in time, that means you're talking about infinitely many compoundings per year. So the question is, what happens to that formula, the big formula at the top of the page, if you send n to infinity? That's the question. What happens to the formula? I'm just going to write the right-hand side. And unfortunately, I can't answer this for you rigorously without using some calculus. So I'm not going to answer this for you rigorously. I am going to answer it for you, but there will be some parts here where I have to like wave my hand and tell you, you just have to believe me just a little bit. I promise, just a little bit. We've seen this sort of notation before when we talked about asymptotes. Remember, like as x goes to infinity, y goes to whatever, or end behavior for polynomials. What I'm asking is, what's the end behavior for this function when I study it not as a function of t, but when I think of the variable as being n? Right, so I don't really care about r. I definitely don't care about p. He's just a constant outside multiplying this thing. T is an interesting variable for this, right? But the t only shows up out here, so it's like something raised to the t. What I really want to know is, what does 1 plus r over n raised to the n do as n gets bigger and bigger and bigger? And I'm going to aim to answer this question for you as satisfyingly as I can here. And I'm going to do that by ignoring all the other variables. So thinking of a of t equals p times 1 plus r over n to the nt as a function of n, set p, r, and t all equal to 1. And we want to study as n goes to infinity. So what did that give me? That would give me 1 plus 1 over n to the n. And I want to study this as n gets bigger and bigger and bigger and bigger and bigger. So what I'm going to do is make a little table. And I'm going to plug in orders of magnitude, powers of 10. And one more. A fun thing to do, if we were sitting in class here right now, I might ask you to do this, is to take your phone number and plug it into this thing. Right? Take n to be your phone number, your 10-digit phone number, right, including area code, and plug it into this thing. You'll see something funny happen. But I'm just going to go ahead and do these calculations. I'll use Desmos. Things go a little more quickly. Turn on my timestamp. I got a funny feeling we're getting close. Running out of time. Okay. So first, in order to I'm just going to give this thing a name in Desmos so I can work with it. So I'll make that easier. Don't worry about the graph. I'm not worried about the graph. I just want to calculate some values. So if you plug 1 in here, what do you get? Well, you get 1 plus 1 over 1, all raised to the 1 power, right? There's an n out here in the power. There's also a 1 over n inside the base. It's a weird function. I want to point that out also, right? This is not a polynomial. This is not a rational function. It's not an algebraic function of any sort. It's also not a standard exponential function because the inside also has a variable in it. So thinking about this as a function of n, it's a very weird function. So don't be worried about that graph. But when we plug 1 in, we get 2 out. Because 1 plus 1 over 1 all raised to the 1 power is 2. If I plug in 10, then I've got 1 plus 1/10. Okay, that's 11/10. Sorry, 1 plus 1/10 is 10 over 10 plus 1 over 10 is 11 over 10. But then I need to raise that whole thing to the 10th power, and that's not something I want to do by hand. I get 2.25. It's nice, it works out like that. If I plug in, oh no, not f, sorry, so sorry. This is not 2.25. I don't know why I typed 2 there. We're plugging in 10. 10. There we go. 2.5937, blah, 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 blah. I'll call it 2.59. This is something people actually did by hand back in the day. But we can do it much faster. If I plug in 100, I get 2.704. We'll call it 2.70. If I plug in 1000, I get 2.7169. So I'll call it 2.72. If I plug in 10,000, I get 2.718145, blah, blah, blah. I'll give you a few sig figs here, 2.7181. And let me go one more. Let's plug in 100,000. 2.718268. 18268. Do you notice anything about these numbers? Let me come back to the 1000 and give you a few more sig figs here. It'll help. So that was actually 2.7169. So 2.59, 2.7, 2.7169, 2.7181, 2.718268. These numbers are getting closer and closer to something. If I plug in some astronomical number, I'm getting rounding errors now, aren't I? Yeah. If I plug in a big number that is just about as big as Desmos can handle without pooping itself, you get 2.718282. So as n goes to infinity, this thing is approaching some specific number, and that number is called E. And it's about 2.71828. This number is called E. These days we say it's named after Leonard Euler. That's not really the reason that was called E originally. I just learned that recently myself. I always assumed it was named after Euler. But this is a special constant. It's a very important special constant. For reasons that you'll learn in calculus, using this number as the base of your exponential function is kind of the nicest base you could possibly use, right? So 2 to the x is fine. 2 to the x doubles every time x goes up by 1. 3 to the x triples every time x goes up by 1. E to the x does something very special with respect to the calculus operation called the derivative. Remember, we've talked about average rates of change a few times in this class, and I hinted that there's something called an instantaneous rate of change. The instantaneous rate of change for e to the x is e to the x. It's very special. So some facts about this number. It is irrational. In fact, it's one of the special irrationals that I mentioned the other day. It's a transcendental irrational. It's called the natural base, or Euler's number. Leonhard Euler was probably the most prolific mathematician to ever live. Famous man, Swiss-Austrian mathematician around the time of the American Revolution, lived around the 1700s. He went blind, completely blind. And for the latter half of his life, he basically just sat there totally blind, dictating mathematics. And it was true. Euler was a brilliant man, solved many, many, many important problems in number theory and analysis, things that you would never think anybody would figure out. He figured out, for example, how do you add up 1 plus 1/4 plus 1/9 plus 1/16 plus 1/25, on and on and on forever. The sum of the reciprocal of the squares. He found that number is pi squared over 6. Brilliant man. So many things. So we named the number after him because a lot of his work revolved around it. You can think of it that way. So it's called the natural base, or Euler's number. This name, I know it looks like it should be pronounced Euler, but it's not. It's Euler. This is German. What else do we want to say about the number E? That's enough. I will expect you to know that it's around 2.7. I don't expect you to memorize a bunch of sig figs, but you should know that it's about 2.7, right? A little bit smaller than 3. That's the level of precision I'm going to ask you. And we think of the function f of x equals e to the x as a very special exponential. And values of e, like powers of e, the things that this outputs are not nice numbers. E is itself an irrational number, a transcendental irrational number. So any integer power of e is also going to be an irrational number. So when you're talking about the numbers that come out of this, like when you plug in 2 for x, you get out e squared. Just call it e squared, right? Don't fuck around with the decimals. The graph of this function. Since e is bigger than 1, this is going to be a growing exponential. So it has the horizontal asymptote over here on the left. And it looks like every other growing exponential. You have here the point 0, 1. You have here the point 1, e. You have up here the point 2, e squared. And I think e is pretty close to 3, so e squared should be pretty close to 9. That's about the logic you need to apply. Over here, you would have the point -1, e to the -1, or 1 over e. And you approach this horizontal asymptote, y equals 0. It's the same as all the other exponential graphs, but it is a special one. It is the right base to use. Even though these numbers that are the y values that are coming out here are not as nice as the y values that come out of 2 to the x or 3 to the x or 1/2 to the x even, this is still the right one. You know that all the exponentials are kind of similar, right? They all have like the same shape. So you want to just pick one and use it all the time. This is the one, because it does that thing with the calculus operation so nicely. Okay. What does this do to our interest formula? Just a little side note. As n goes to infinity, a of t goes to this new formula. I think in college algebra, we call it C of t, C for continuous compounding. It's the principal times e to the RT. The fact that t is in the exponent here, that's not weird. you've got, p times 1 plus r over n all to the nt. And you know that the 1 plus 1 over n to the n stuff all goes to e. So it should be like e to the t. The fact that an r shows up right here, that the r from r over n makes it into the exponent, that's kind of interesting. And that's the part that I really can't prove to you without using some calculus. This is called the continuous compounding. Continuously compounded interest. And I know if you took college algebra here at Santa Fe, definitely you got the stuff beaten into you pretty hard, but I also suspect that you probably didn't get a very good explanation for where it comes from. So I hope that this settles some of that stuff in your mind if it was bothering you. What do you guys need to know in this class? You need to know that E is about 2.7. It's an irrational number, and you need to know what the graph of e to the x looks like. That's about it. All right, that's what I'm going to require of you. You need to be able to work with this function and this graph. When you write down these powers of e, or when we solve equations involving this function or this number, please just leave them as e's. All right, do not put the stuff into your calculator and give me decimals. I don't want decimals. I just want you to leave powers of e as powers of e, even if it looks weird or scary.
How involved is this in Calc 1?
Very intimately. Perhaps the most important function in all of calculus right here. It also connects to trigonometry in a way that's going to fucking shock you when you see it in Calc 2. If you plug non-real complex numbers in for x here, if you plug the number I in here, or 2i, or I times pi in here, you get trig functions out. I know it's weird. But yeah, this is intimately connected calculus. Pretty much, I've never written a calculus test that doesn't have the number e on it somewhere. They all do. And when you talk about the two main calculus operations, which are integration and differentiation, this is like your fixed point. This is like home base for that stuff. So hugely important. The continuously compounded interest thing, this is up to the professor, how interested they are in those particular kinds of application problems. I find that shit boring as hell. I'm not a banker. I don't think most of you are bankers. If you are a banker or an accountant, please don't hate me. But I'm way more interested in the mathematics. So I'm not going to beat you guys to death with any interest stuff. But the function e to the x is going to show up everywhere in calculus. All right. So unfortunately, there's not a whole lot I can make you do with this function yet, except ask these interest problems, which I, again, find boring as hell. So the purpose of all this is just to get us to the number e and talking about the function e to the x, which means we're ready to introduce a logarithm now. And that's what I'm going to do in the next few minutes. I'm going to motivate the existence of logarithms and define them for you. I mentioned a few times solving equations that have to do with exponential functions as being a goal. So this is our intro to logarithms. And I just want to begin with a question. How would you solve 2 to the x equals 3? Is there even a solution? Our brains, when I first saw this, my brain started going like, well, can I take some kind of root? Is there some sort of algebra operation I can do to get x alone? And you run through all the algebra operations, can I divide by 2? Will that work? Well, no, if I divide this by 2, the x isn't going to go anywhere. If I take the square root on both sides, the x isn't going to go anywhere. None of our algebra operations have the ability to get this variable down from a power. And eventually logarithms are what are going to do that for us. You can try plugging in some numbers for x. If you plug in 1 for x, you get 2 to the 1. Well, 2 to the 1 is 2. That's smaller than 3. If you plug in 2 for x, 2 to the 2, that's 4. That's bigger than 3. So I can start to speculate that if there's a solution to this equation, it's somewhere between 1 and 2, right? Plugging in 1 gives me something too small. Plugging in 2 gives me something too large. And if you look at the graph of 2 to the x, you know what he looks like, right? Here's every growing exponential. You know, this point is 0, 1. This point is 1, 2. This point is 2, 4. So if I throw in the line y equals 3, it's right here. And we can see that there is a solution to that equation. This x value is the solution to 2 to the x equals 3. It has to exist because those graphs do touch. But finding it, that's a little tricky. In fact, it's very tricky. Let's see, can I sneak this in on you guys? I think I can. Yeah. Okay. That's about right. Yeah. So let me clear this out and take a look at these graphs here. Y equals 2 to the x. Y equals 3. Definitely there is a solution. And I claim that that solution is about 1.58496. See, if I plug 1.58496 in for x, 2 to the 1.58496 is like 2.999999. Very, very, very close. So I claim that the solution, which is hard to find, is x equals approximately 1.58496. Now, in fact, the exact solution is an irrational number, so I can't write out it in decimal form. And really, the nicest way to characterize this number is as the solution to 2 to the x equals 3. But there's a special notation for it. I will introduce that notation next time. But before I let you go for the day, I'll tell you that finding this solution let me come back in here, right? And indeed, two raised to the 1.58496 is like, I'll just write down 2.9999. I think we had at least 4 9s there, right? And there's a 4 somewhere. It's very, very close to 3. All right, so finding the solution is all about finding an inverse function to the function f of x equals 2 to the x. And that function is called a logarithm. All right. In fact, the inverse to any exponential function is a logarithm function. And just like you have a bunch of different exponentials with different bases, this would be called a base 2 logarithm. And I can draw its graph because we know how to graph an inverse function from the original function. Right, so if here I have the original function y equals 2 to the x with his horizontal asymptote here, and some points like 0, 1, 1, 2, 2, 4. Let me get some points over here too. This would be -1, 1/2. And this point right here would be like -2, 1/4. Oops, sorry, here we go. Here's the graph of 2 to the x again with a few extra things labeled. You remember how to write or how to sketch the graph of an inverse function from the graph of the original. You take the original and you reflect everything neatly over the line y equals x. Right? Because that's what the inverse does, is it swaps all the x's and y's. So the graph of this inverse function, which we said is called a base 2 logarithm, is going to have the point 1/4, -2 on it. It's going to have the point 1/2, -1 on it. It's going to have the point 1, 0 on it. It's going to have the point 2, 1 on it. It's going to have the point 4, 2 on it. It's going to have a vertical asymptote where this one had a horizontal asymptote. The inverse, when you flip everything over this line, is going to have a vertical asymptote. So it's going to look like this. This is the base 2 logarithm. And we were able to graph it without doing any algebra at all, just taking the graph of 2 to the x and reflecting it over the line y equals x. This was something we did back in section 2.8. We talked about inverse functions. I will talk about the purple function a lot on Wednesday. All right, on Wednesday, we transitioned to talking just about the purple function. We've been talking about the black functions for about a week now. These logarithm functions, they're nice in the sense that they are the inverse of a very nice function, right? 2 to the x and exponentials in general are very, very nice functions. They're not nice in some other senses, right? Exponentials have domain all real numbers. They'll take any number you want and they're happy. Logarithms, their domain, there's nothing over here. And they have a vertical asymptote, which are kind of problem points, right? Those are places where a function is undefined. So the logarithm, his domain is just 0 to infinity, right? Open interval 0 to infinity. It's the range of the exponential. His end behavior is kind of weird. As you go off over here, he gets shallower and shallower and shallower, but he does continue to grow. He just grows very slowly. So this does go to infinity, like in the up direction. It just takes a shitload of time to get there. This grows exactly as slowly as this grows quickly, right? Again, inverse. So however fast the black grows is how slow the purple grows. And the horizontal asymptote from the black becomes a vertical asymptote for the purple. And again, vertical asymptotes are kind of unpleasant in a sense. But this is all I'm going to say about logarithms for today. On Wednesday, I will give you the formal definition of a logarithm. I will show you how I came up with this number, x equals 1.58496. That got me so close to 3 when I plug it into 2 to the x. There's going to be a lot of notation and a lot of algebra, so please come ready. If you haven't done this yet, I think I asked you guys to last week, but if you haven't done this yet, please go back to section 2.8 in the book. Just literally open the book. If you don't have a physical book, go into WebAssign and open the ebook. Go back into section 2.8 and look a little bit at inverse functions. I'm thinking specifically of the TFAE, where you said, A comma B is on the graph of F means B comma A is on the graph of F inverse, and what that says about domains, ranges, all of that stuff. And make sure you're comfy with this idea of flipping the graph over the line y equals x to get the graph of the inverse, all that. Please brush up on that shit so we can move at a reasonable pace through section 4.3, which is logarithms. After that, we're going to talk about algebra properties of the log, and we're going to start solving equations using the log. So it's going to be fun stuff, but it's a little bit tricky. Just bone up on inverse functions and make sure you've done the exponential homework and you'll be in good shape. All right, I'm going to end it here for the day. I hope you guys have a lovely rest of your day, and I will see you all on Wednesday.